Light is an electromagnetic wave. What does that mean? Everywhere in space there's an electric field and a magnetic field. And to produce light, those fields oscillate perpendicular to each other. Here's one row of points in space. There are plenty of other points outside this row. We're just going to focus on this row for now. Standing in its way is a polarizing filter. If I send vertically polarized light through, it passes right on to the other side. And the reason is because this filter has a vertical transmission axis. You can think of the transmission axis as a thin window that either allows the oscillations or blocks the oscillations. What if we take this filter and we make it horizontally polarizing? Well, now, this filter only transmits horizontal oscillations in the electric field. So our vertically polarized light doesn't make it through. What happens? It gets absorbed by the molecules, and the molecules of this filter start vibrating. So the light energy converts into internal energy of the filter. But what if we take this filter and we make the transmission axis at an angle? What happens? Does some get through? Which way is it oscillating? How much is there on the other side? To answer these questions, we're going to imagine taking all of these oscillations and we're going to project them all as a single arrow on this screen or this filter. It's almost like we're watching a projector screen or watching the shadow of all of these oscillations. If we look at this head-on, we have the maximum electric field oscillations, and we'll always mark theta between the oscillations, the polarization plane, and the transmission axis. Now it might be a little easier to see how much of this gets through. Any part of that electric field vector that lies parallel to the transmission axis, any such part transmits. Well, how far does this vector extend along the tilted green axis? Let's draw an arrow showing the component of the amplitude along the transmission axis. It looks like this. And let's draw another tilted component, one that gets blocked. Any light perpendicular to the transmission axis doesn't pass through. So is there any part of this purple vector lying on this tilted y-axis? Yeah, there's this part right here. The green component of this amplitude passes through to the other side because it's parallel to the transmission axis, and the red component gets blocked and absorbed because that component is perpendicular to the transmission axis. Having tilted components and using tilted axes might seem odd, but don't forget it's exactly what we did when we studied forces on an incline. Gravity points down, but we didn't use traditional x and y axes. We used tilted axes, and then we drew components pointing on those tilted axes. It's the exact same thing that's happening here. Just as gravity was the hypotenuse with these tilted components, the electric field amplitude here, that's the hypotenuse with these two components. So the next question is, which component is the cosine component and which one is the sine component? Cosine is adjacent, so green, that's the component that uses the cosine, hypotenuse cosine theta, and red, that's the component that uses sine. So remember, we don't really care about red because green is the one that gets through. And we're taking this amplitude, this maximum electric field strength, we're multiplying by cosine. But unfortunately, we won't really deal with amplitude, we will deal with intensity. And intensity depends on the square of amplitude. So if we multiply the amplitude by cosine theta, then the intensity gets multiplied by cosine squared of theta. That is precisely what Malus's law says. Malus's law says that the transmitted intensity, I, is equal to the initial intensity striking the filter, I0, multiplied by the square of cosine of theta. And remember, theta is always between the polarization plane and the transmission axis. So we could take Malus's law and we could divide by I0, and what we have on the left then is the percent of intensity transmitted through the filter. Let's see how this works out in problems. Here is a filter, and here is some vertically polarized light. We send it through the filter. And let's say the angle between the polarization plane of the light and the transmission axis, that angle is 45 degrees. The question, how much light is transmitted? We can use Malus's law, and we'll use this form in particular. Remember that to find the percent transmitted, we use the cosine squared of theta. And in this case, the angle is 45. The cosine of 45 is 1 over radical 2, and you can draw a triangle to figure that out. But when we square this, we get that the intensity, which makes it through, is 50% of whatever strikes. So when the angle between these is 45, half of the intensity gets through. Would the answer be any different for these scenarios? Here we have horizontally polarized light, but again, the axis is at 45 degrees to the horizontally polarized light. Here, again, it's a different scenario, but they're still at 45 degrees to each other. Same thing down here. In every scenario, we have the exact same answer. The angle between the polarization plane and the transmission axis is still 45 for all three situations, so half the light still gets transmitted through. And let's not forget, not only will this electric field be oscillating with less intensity, it will also be oscillating in a different direction, because the new oscillations have to be parallel to the transmission axis. Consider this scenario. The sun emits unpolarized light which falls upon 3 filters. The unpolarized light does not follow Malus's law. Instead, we know a different rule. Half of unpolarized light passes through any polarizing filter. What happens next? Well, the light is not oscillating exactly in line with the transmission axis, so only a component of this oscillation gets through. What happens next? Well, this new oscillation is not exactly in line with the transmission axis, so only a component, some part, will pass through. If we say that the initial intensity is I0, we know that half of that makes it through this polarizing filter. That's the rule for unpolarized light hitting a filter. What about this scenario? Well, pretend that this is a 45-degree angle. And what happens? This initial intensity striking the filter will get filtered again by half. So it becomes I0 over 4. Then let's imagine that again, these two things are at 45 degrees to each other. Now, this is the incident light striking the filter, and only half will pass through, so we cut it down once more. The final intensity of this initial unpolarized light that makes it through all 3 filters, each angled at 45 degrees to the prior filter, the final intensity making it out the other side is I0 over 8. For final scenario, consider this. We have 3 filters, but they're not turned at 45 degrees to each other. We have vertically polarized light falling upon these 3 filters. We know that each filter will reduce the intensity, so the oscillations after this filter are a little bit smaller. And again, this filter reduces the intensity because there's an angle between the two. And so the oscillations are a little bit smaller, a little less intense. And then when this when these oscillations pass through this filter, again, because the polarization is not perfectly aligned with the transmission axis, there's some filtering that occurs, and the subsequent oscillations are slightly less intense. But the question, of course, will be, how much less intense? So let's say that we're given this information. The first filter is at 20 degrees from vertical, and then the next filter is at 30 degrees from the first, and then this final transmission axis is 40 degrees from the second. The initial intensity is 12 watts per meter squared. Okay, we just plug away with our formula. To find how much gets transmitted, we multiply by cosine squared. So for the first case, the angle is 20. We square the cosine of 20, and we get 0.883, which is the same as 88.3%. All right, so 88.3% of the 12 makes it through, and that gives us a value of 10.6 watts per meter squared as the new intensity. And then we apply the next filter with its angle of 30 degrees. Remember, 30 degrees is the angle between the polarization plane of this light and this transmission axis. So we do the calculation and we get 0.75 or 75%. 75% of the green makes it through, and that gives us a value of 7.95 watts per meter squared. And then we do this one final time. We plug in the angle of 40 degrees between this polarization plane and this transmission axis. We get 58.7%. And when we apply that percentage to the incident light, what do we get? A final answer of 4.67 watts per meter squared. Now, a quick note, the light is not actually changing color as it passes. This is just my way of distinguishing the different stages. The color would be unaffected by this procedure. Now, we can do this step by step like you've seen, or we can find how much is transmitted by starting with the total intensity and then applying each filter in succession. This calculation gives the exact same final answer. So this video introduces Malus's law and a couple of ways to think about it, and it also gives us some introductory calculations and problem scenarios. Thanks for watching.